Thank you for the introduction. I'm happy to be here. Always happy to be in Japan, especially in such a beautiful, special location. Okay, so I will talk about two topics. Essentially, one topic I will focus on some topological aspects associated with non-equilibrium, non-equilibrium magnetic dynamics, and look at some potential utility, one concerning energy storage and another concerning neuromorphics. This is a magnetism talk on short length scales, on macroscopic scales. The systems of interest for me will look like this. They could be ordered ferro, antiferromagnet, could also be some non-collinear ordered system that will look nice on short length scales. On the length scale of a device, in the end of the day, also in the spirit of this program, the system will look more like this, and we will try to make some sense out of this naughty configurations. My focus is going to be on the dynamical phenomena. This is a physics talk, but I always find it kind of entertaining, amusing to also think of potential applications, and who knows, maybe some of them might one day become useful. Right. For this audience, I don't have to emphasize, convince you in the importance of topological features in nature. They're abundant, they're important for material science, for hydrodynamic phenomena, in equilibrium. Topological defects of ordered media are omnipresent and extremely important in dynamical critical phenomena, as well as spontaneously emergent topological features out of nonlinear dynamics are really crucial for understanding sort of true physical behavior, not of idealized systems, but sort of real world systems. And I think it's much in the spirit, of course, of this institute to think about this phenomena, as well as think about potential applications concerning sustainability, etc. So for magnetism, of course, for decades, people have been thinking very hard about topological textures, but it's relatively recently, I would say, last 20 years or so, that various topological textures became rather mundane in magnetic systems. So people can image, people can probe, can manipulate varieties of topological textures in one-dimensional, two-dimensional, three-dimensional systems. I'm referring to things like winding, associated with domain walls, skyrmionic textures. Then out of such skyrmionic textures, if you start with some solitonic objects, you could sort of go higher to higher level descriptions, discuss some crystalline arrangements of some such certain solitonic objects based on topology, some fluid-like dynamics. In 3D, you have Hopfians that Ivan already mentioned, hedgehogs like this, block points. You also have so-called Shankar or three-dimensional skyrmions. So such objects are no longer exotic, easily imaged, and I think the time is ripe to think of applications. If you ask yourself what applications are out there based on topological objects, and specifically focusing on magnetic systems in a solid state environment, one prominent example has to do with so-called it's still a proposal for magnetic racetrack memory based on domain wall, quasi-one-dimensional domain wall of skyrmionic motion. I'm not referring here to a commercial product that you actually can buy on Amazon. It's also called magnetic racetrack. This is still a proposal. It's based on topological features in magnetic wires. However, topology doesn't so dictates the existence, emergence of those solitonic objects based on which you're designing your memory registers. But in the end of the day, the physics is rather mundane, I would say. Once those topological objects are defined, that are treated as essentially some kind of colloidal point-like particle, like a colloidal particle, which is then manipulated in a rather conventional sense. So, by this talk, I want to go beyond that, and maybe at this point it's somewhat dreaming. A lot of things I'll tell you about it. It's rather concerning experiments and applications are rather at the stage of mostly at the stage of proposal at this point, but nevertheless, I want to start thinking about more general hydrodynamic phenomenologies and hydrodynamic phenomena emerging out of topological features in magnetic systems. So some of the hallmark properties that I will build upon existence of extensive topological invariant. For me, that's going to be the starting point for formulating innate conservation laws based on which I want to construct some hydrodynamic description. Bulk boundary correspondence will play a crucial role. Through such bulk boundary correspondence, I will devise means to electrically inject and detect such topological hydrodynamics present in the bulk. And by bulk, the dimensionality could be varied. Could have a one-dimensional bulk, two-dimensional bulk, three-dimensional bulk. So correspondingly, the boundaries would be zero-dimensional, two-dimensional, one-dimensional, or two-dimensional. And then eventually we'll imagine to depositing some electrical contacts for manipulating, injecting, and detecting hydrodynamics, that's topological hydrodynamics that's happening within the bulk of the system. Topological transmutation, some kind of interconversion between different topological features, for example, between winding and vorticity in two-dimensional systems, or between a kind of block point position and skyrmionic textures on the boundaries. Such topological transmutations also will play a key role, and they will kind of go hand in hand with bulk boundary correspondences. For potential applications, I will emphasize two ideas that we have proposed over the last few years: energy storage and some idea for neuromorphic systems. I gave a seminar a couple of days ago at the Institute in Hikashi, Hiroshima, on energy storage. So I apologize to those people who were already at the seminar, but even to those of you who saw my seminar, hopefully you'll see something new in this talk concerning this topic. Okay, so let's start with a high-level picture. The big idea, schematically is shown here. So we have a medium of certain dimensionality, typically 1, 2, or 3, within which there's a natural topological hydrodynamics. In the context of costless physics, it could be some medium that's fluctuating vortex anti-vortex distribution. In the case of racetrack, there could be domain walls sloshing around. In practice, you could be able to image these objects, but let us suppose, for our purposes, because my focus is going to be on electrical devices, let me suppose you can't really directly access these objects other than through the boundaries. And the boundaries, you could do two things, sort of input and output. And I will play those two things kind of in a reciprocal fashion. So whichever mechanism I will devise for the input, I will use Onzaga reciprocity for the output. And I'm interested in interfacing such media with electrical circuitry. So this medium, this black box, is going to be ultimately an element in some electrical circuitry. In that external electrical circuitry, I could apply electrical currents. That electrical current will exchange, will be allowed to exchange free energy as well as entropy between the electrical circuit and this black box. The microscope, I'm not going to dive into microscopic details. I understand this is a rather broad audience, but for the experts here, just to mention some keywords, the basic tools of spintronics, particularly things like spin transfer torque, spin pumping phenomena at the interface that are known now to interface very efficiently electrical and magnetic degrees of freedom. Some kind of variant of spin transfer torque, spin pumping physics, spin multiforces that will be employed at the interfaces. I'll make some general arguments based on symmetry, but feel free, maybe during the breaks, if you're interested, to ask me more details about sort of nuances of microscopics that go in. So to summarize, here within this black box, we have a continuity equation rho. Here is a topological flavor, for example, vorticity. There's some hydrodynamic regime, maybe diffusive regime or hydrodynamic regime that that provide us the basic phenomenology for how this topological flavor is moving throughout my system, and then I will be interested in controlling, injecting some flow of this topological flavor, as well as reciprocally detecting in some non-local fashion.
Excuse me.
Yes.
Do you make a difference between spin and vorticity?
Yes. So microscopically, just to be somewhat concrete, imagine that everything is based on some spin lattice. So the most basic microscopic level, we have a quantum spin lattice. It could be a square lattice with some spin per vertex of the lattice. But I'm not interested in detailed spin dynamics. Rather, I'm interested in some kind of coarse-grained dynamics of topological flavor associated with with spin configuration. So imagine some vortex, etc. Okay, so one example of that.
Just another quick question. What you refer to as spin flavor, can I think of this?
Topological.
Can I think of this as a topological charge?
Yes.
Is there a difference?
Yes, it's a topological charge. Right. So perhaps the simplest example of that is winding. Imagine a magnetic XY model, could be easy plane, ferromagnet, or antiferromagnet, or even classes of non-collinear systems that effectively map onto some kind of planar XY model. It will be some natural winding configuration. The snapshot of that winding configuration can look like this. Now, spintronics gives us means to drive the boundary of such a system out of equilibrium by applying electrical current, for example, using the so-called spin Hall effect that generates out of equilibrium spin accumulation in this metal polarized out of the plane. That out of equilibrium spin accumulation then exerts a torque on the magnetic order parameter, and that torque would input work into magnetic configuration in proportion to some winding with a given handedness. So winding, let's say clockwise winding, gains energy from the external electrical circuit. Anti-clockwise winding loses energy. So that basically performs this kind of operation. You could electrically, controllably start winding up magnetic order parameter at the boundary, and that winding will propagate hydrodynamically downstream because the net winding over the system is conserved. So it can propagate, it can slosh around, and maybe come out elsewhere in a kind of strongly ordered XY regime. That is very much phenomenologically very much similar to what happens in a one-dimensional superconductor. If you inject electrical current into the superconductor, the action of the electrical current injected at the end of the superconductor looks very much like this, except rather than the spin, you have electrical charge. Rather than magnetic order parameter, you have the phase of the superconductor order parameter. The essential phenomenology is the same, and the microscopics also looks very much similar. The spin torque microscopics looks like this. You have some spin impinging polarized out of the plane, reflects as from some configuration of spin polarized into the plane. Some angular momentum is transferred into this magnet that could be insulating. It looks very much like Andreev reflection for people who are familiar with what happens at the interface with the normal metal and the superconductor. That's just a little example, just conceptual warm-up. But now I'm going to build up a little bit. I'm going to consider a couple other examples, and then try to already start dreaming up about devices and some practical utilities based on this physics. Okay, so the other example concerns injecting vorticity in a two-dimensional magnetic field. So now we have a two-dimensional film, we have electrical wire, electrical contact that interfaces, let's say, a left boundary of such two-dimensional film. Let's make it also magnetic. just to have some handles on the symmetries of the system. So it's a metallic magnetic wire, polarized with magnetic order parameter here, polarized out of the plane. And this is, again, an XY system, but now I'm focusing on vortices, anti-vortices proliferating. We might be close to KT, BKT transition. For example, that would be an interesting place to look at the proliferation dynamics of free or nearly free vortices, anti-vortices.
Question,
Yep.
So in this case, the vortices, there be plus and minus going in
Yes.
opposite direction?
Yes, exactly. Right. So this system now will be like kind of like a semiconductor with two carriers of opposite charge. In a superfluid, of course, we'll have like world expert on KT physics. I love talking to David about anything related to this kind of physics. In a superconductor, you would probably have symmetry with the vortices and the vortices. In magnetic systems, typically the symmetry is broken. So usually vortices are more natural objects, they're more mobile, and the vortices are kind of more clumsy because of static interactions or transfer interaction. So we still have two flavors in the system. Thermodynamic limit should be neutral, but one of the flavors, let's say plus vortices, would be typically more mobile, let's say, than minus vortices. Some extreme case, you could even treat the anti-vortices as a frozen background, so it will be kind of like a jelly model type of thing.
Thank you.
Yeah. So again, I'm not diving into details here. Just want to kind of create a few pointers around which I can sort of start building something interesting. So the key aspect here I want to emphasize again, based on a sort of very basic, well understood in spintronics spin transfer torque physics, I want to create a kind of Magnus force on these vortices at the interface. So at the end of the day, I want this electrical current to act on the vortices in the vicinity interface, like basically as Magnus force of some hydrodynamic flow acting on some rotating object. Of course, the microscopic details are very, very different, but sort of the cartoonish picture of what is happening at the interface, I want to think of it like this. It's really a Magnus force. And of course, if this current creates a Magnus force on vortices, whatever outflow of vortices on the other end will create a reciprocal effect that could be detectable as a voltage in non-local voltage generated elsewhere on the detection side of this device. A basic torque of this form, where little m is predominantly in plane order parameter for this blue region, the capital M, the order parameter in the contact, J is the electrical current pointing in the y direction. This is some logical prefactor. This kind of torque acting on the spontaneous magnetic dynamics, spontaneous or driven, maybe thermally driven, or even quantum mechanically driven magnetic dynamics at the interface. This is torque times angular velocity at the interface integrated over the length of this interface. That turns out to result in this expression, triple vector product within Z, normal to this plane, electrical current in the y direction. J is the vorticity current in the horizontal direction. Appropriately defined, I'm kind of hiding the technicalities, but that's the vorticity current is appropriately defined in terms of little m. So such input of power into the system is precisely what I want to realize this kind of picture. So basically, a cross flow of electrical current and vortex current of a particular relative sign will gain energy from the supplied electrical power in this device. So that's the input of energy, and then I have continuity equation for vorticity, which I can consider as a kind of plasma, or sort of disordered plasma, and look at the response, transport. I can play games very much analogous to, for example, the kind of phenomena that you're familiar with in semiconductor physics. And in the end, it's not too different from the example in the previous slide. So these two examples show two cases which are rather practical based on the state-of-the-art tools of spintronics on the one hand. On the other hand, you could anticipate generality of such simple ideas in relation to various topological textures, not just winding and vorticity, but also hedgehogs, fermions, pretty much any imaginable texture that underlies some extensive topological hydrodynamics. Okay. All right. So in the next 5 minutes or so, let me just quickly flash two conceptual applications that I can build on this physics. One is energy storage. The other is a proposal for spiking neural network based on control and dynamics of such topological flavors. So for energy storage, we imagine a device that basically does what was sketched in this picture. You have some quasi-one-dimensional magnetic spiral that you can twist, input some free energy into this spiral, and output that free energy through some electromotive force. Well, how to do it in practice? In practice, one potentially practical device that we are not too ashamed to discuss with experimentalists looks like this. It's a bilayer. It's topologically, it's very much similar to the device I've shown, or the system I've shown on the slide with the Magnus force and vortex dynamics, just slightly different geometry. We have a bilayer. Now the magnetic film, now in the shape of the annulus, within which we have vortex dynamics, is lying on top of an annulus made out of the metal contact that is itself a magnet with magnetization polarized out of the plane. We need that to lower the symmetries so that the electric current in this blue region can basically exert Magnus force on the vortex and dynamics the way we want it to work out. So in the device, the basic bilayer structure with a hole in the middle, with this topology, electrical current circulating around this blue region. From the symmetry point of view, you can convince yourself that vorticity flow outward in the radial direction in this red region is allowed from the symmetry point of view, and microscopically it's related to the kinds of torques that I've already discussed. From the point of view of basic phenomenology, if I want to map it onto electrical circuit, some effective electrical circuit, I'm thinking of such cross-coupling between electron flow in this blue region azimutally and vortex flow in the red region radially. The key physics for my coarse-grained kind of device behavior boils down to relations, so Onzaga relations of this form. I have electrical current I circulating like this. I have vorticity current IV circulating in the radial direction. They have some impedances for their own motions. This is ordinary ohmic resistivity. This is an analog of the ohmic resistivity for vortex motion. The kind of objects that have been involved many years ago by people like David in the context of, for example, dissipation and superfluid films associated with the motion of vortices. So this is some impedance and some dissipation associated with vortex motion. The key here is such cross-coupling, such Magnus cross-coupling, Onzaga reciprocal Magnus cross-coupling between such two fluxes. And V and vis-a-vis are the thermodynamically conjugate forces, like voltage, electrical voltage, and an analog of the vortex voltage. So the basic idea here, we have, just to summarize, no time to get into details, we have the essential Magnus cross-coupling of this form between electrical degrees of freedom that plug into some external circuitry, and a more abstract topological degrees of freedom that, even though we don't have direct access to, they're sort of sitting there and performing some interesting functionality within our device. Now, the specific device we're focusing on is energy storage. Here, that energy storage is based on applying electrical current, generating vorticity flow radially. That builds up winding azimutally, and that's the energy of that winding. The free energy of that winding is essentially effective capacitance of topological flavor, where we're going to store the energy. The energy is taken out of the system by Onzaga reciprocal process. So we'll let those vortices we'll let the winding to relax. That's what happens in a low dimensional superconductors. When the natural superflow relaxes, the transverse flow vorticity associated with the natural relaxation of the winding is then ejecting energy into the electrical circuitry. That's the basic idea. one point in terms of the efficiency of such devices, one point that I like emphasizing is that the basic thermodynamic efficiency of such devices mathematically follows very much the structure of efficiency of thermoelectric devices. So there's a figure of merit that is, we call it a kind of topological ZT. ZT is a figure of merit of thermoelectric devices that is proportional to gamma square and inversely proportional to the product of R and RV. Like the ZT is proportional to thermal power squared, for those of you who are familiar with thermoelectric devices. So we formally can map the basic phenomenology onto what is very much known and familiar already from the thermoelectrics, at least formally, in terms of basic thermodynamics. Okay, let's skip this and just maybe a couple of minutes for questions. Here I have time just to advertise the idea that we have for building spiking neural network based on spatio-temporal winding dynamics. Again, I'm back to the most elementary example of topological hydrodynamics. So I imagine various channels. Some of these channels, so there's magnetic strips in various modalities, in various physical modalities of winding dynamics. Some of these strips will realize synaptic behavior. Some of these strips will realize kind of axon behavior that can transmit solitons, on ballistic, in some extreme case, solitons. And then kind of local, the temporal dynamics will realize some switching of a neuron. So imagine, okay, this is a neuron. This is a little droplet of a monodomain planar dynamics. Let me focus on antiferromagnets. All of this, the supposed order parameter, and all of the elements here will be anti-ferromagnetic, but different elements will be in different physical regimes. Okay. Okay. So the basic idea is again we have a topological flavor density given by the winding density of the order parameter. So phi is the polar angle of this xy order parameter. That's the winding density. That's the flux associated with the winding density. Together they obey continuity equation. And imagine this is a channel that brings in a signal, some proliferating texture that's impinging on a neuron, quote unquote. The neuron will integrate this signal. There's some easy axis anisotropy. So in equilibrium, it's pointing, let's say, on this axis. Then subject to some critical input of the incoming signal, this neuron will perform leaky integration and phi, and then click. That click will produce a topological output. It's a pi click. So that will eject a domain wall and have some sign coordinate distribution for that domain wall that will propagate ballistically through an axon, and then the process will continue. Okay, that's the basic idea. And then around this idea, you could sort of fantasize. So this is our artistic depiction of our fantasy. That's an antiferromatic neuron that's clicking. This is the axon that's transmitting sort of signboard on a soliton that is triggered by the click. There is in a different modality of one-dimensional winding, one-dimensional wound-up magnetic configuration. We have a synapse that would change its weight depending on the timing of this input signal that is impinging on the next neuron. And depending on the relative timing of sort of the input and the output, the weight of the synapse will change. And you could imagine. Let me skip the details. That's where sort of the more specific physics calculations take place. Let me skip those details. The basic spin transfer torque physics actually goes back to some work from my PhD times. Is implemented. Here, leaky integrate and fire. In the end of the day, we believe in all of the ingredients the way at least I understand what is happening in biological and neural networks. All the basic ingredients seem to be in place. So I hope the experimentalists, would be now motivated to pursue such systems for really complicated networks, starting with maybe simple energy storage devices and going up to something as complicated that as a neural brain imitating neural networks. Thank you for your attention.
More questions, yes.
Thank you very much. Very interesting idea. Just I want to ask you the efficiency of the coupling between the topological object to the linear matter, for instance, the electric current or electric voltage. How the efficiency could you enhance the efficiency coupling between the topological object to the
exchange coupling?
Yeah.
So microscopically, the basic interaction we're focusing on is exchange.
Yeah.
However, we
No, no,
typically spin
Yeah,
exchange,
coupling between the topological object to linear matter.
like electrical current,
Electrical.
right?
We need normally we need a spin-off coupling like that.
That's
The
true.
efficiency,
Not always, but often this is the case. Yes.
efficiency, energy
Right.
transfer efficiency is very,
Right.
very low
Of course.
normally.
Right. Of course, these details I'm omitting within this talk, but of course, this is the efficiency.
Yeah.
Like for example, this parameter, this gamma parameter that parameterizes cross-coupling strength between topological and charge fluxes. You're right that often, not always, but usually they are rooted in spin-orbit interaction.
Then my question is, how solve this problem?
It's it's one of the central problems in spintronics in general, enhancing spin-orbit induced spin transfer torque, spin motive forces at the interfaces. So it's a big ongoing problem that is investigated. There are many groups optimizing the various ideas.
But maybe you have very special ideas.
Yeah, well, let's discuss it during the break. Yeah, there are many ideas to be discussed.
What was your bulk boundary correspondence? Was that just counting degrees of freedom? Or
So yeah, for example, for vortices, that's correspondence between vorticity and winding. So the idea is, vorticity is the flavor that we want to control. It's conserved unless the vortices pass through the boundary and then the winding on the boundary is changing. So electrical current at the boundary is actually coupling to the winding on the boundary. So by coupling to the winding, we automatically kind of load or offload the vortices from the system. That's the work of boundary bulk correspondence that I was alluding to.
Thank you. All right, thanks very much again.
Thank you.